Optimisation, one of the most useful applications for derivatives. So as I was saying, it's often called max-min problems. Probably the most common one is finding the maximum. Okay, so it's split into like just abstract questions and like real life questions. So you guys remember yesterday, what did we do?
We did stationary points.
Stationary points, okay? So we're going to follow on from that stationary point topic. Bike. So if this is a quadratic equation, I don't know, x squared plus 3 or something. The stationary point is the point where the gradient is 0. So you find the stationary point, you then all the values around the point to determine if it's a max or min. Okay? So that's arbitrary. It's not really relevant to anything in real life. So that's one type of problem you could get, you know, on an exam, I suppose. Optimization is actually really useful in life as well. So a really common example is geometry. So I don't know, a ship, and you want to get, with the resources you have to build the ship, you want to get the biggest ship you can get. So you want to optimize, you want to find the maximum area of that ship. Okay, so that's the real life application. So I'm going to do an example now of the first type and an example of the second type, a real life application. Okay? So there's some notes if you want to go back and read them later. So here's the first example. Okay, so like yesterday with the stationary points, first step, find when the rate of change is equal to 0. So we need to find the derivative. So y dash, what's the derivative of that? Pretty easy. Yeah, 1, so the x becomes 1, the 0.03, x becomes 0.06x. Okay, so we're going to let that equal to 0, because that's going to give us our stationary point, or the point when the gradient of the curve is 0. Perfect. So we're left with x equals 1 over 6 over 100. X is equal to 100 over either side of that x value used. So we're looking at the x value either side of 16 2/3, where the rate of change is 0. So we're going to sub in. Let's start with x equals 16. Our gradient at x equals 16, is it positive or negative? Positive. It's positive 0.04. All right, let's try when x is 17. Yep. So the answer is 0.02 for the gradient there. So it's a negative gradient. So if you imagine the hill, it's going up, it's a positive gradient, then it has its stationary point, 0 gradient, and then it goes down again. So the rugby ball is going up, stops, and then goes back down again, which is pretty like obvious, hopefully. You know, when you throw a ball, it goes up and then down. So the gradient is positive, then 0, then negative, therefore it is a max. Ball, have I finished yet? I verified that I did this bit. I verified that it was a maximum. It still wants us to do what? Find how good this rugby player actually is at throwing the ball. So what is the max height? How do we do that?
Would we sub 16
Correct. So in this trajectory of the ball, we're finding the max height, so we're putting that 16 2/3 into that. I keep forgetting the equation. X take 0.03 x squared plus 3, I think, for the 3 meter tall rugby player, apparently. I guess if he's 2 meters and then throws it like that, it could be 3 meters.
Well, yeah, what's that?
11 1/3 as the max height. Statement, because it's real life, is the max height.